Hello and welcome to Lecture 7 in Electrochemistry. Today we're going to look at Voltaic cells. Of course, these are the knowledge outcomes prescribed by Alberta Learning. They form the basis for the bulk of diploma exam questions that you'll see at the end of the term. I would refer you back to this page from time to time to get a sense of how your progress is coming. An electric cell, or a Voltaic cell, is a technology that converts chemical energy into electrical energy. The battery is slightly different. The battery is it's essentially a series of Voltaic cells joined together in series to increase the voltage. And we'll explain that here in a minute. Modern batteries continue to be made the same way they've been made historically. Typically they include an electrolyte, which is either an aqueous solution or a moist paste through which electrons and ions can flow. They also include two electrodes. They're typically made out of metals, or one's a metal and the other's an inert graphite rod. Some batteries are manufactured so that the battery casing itself is one of the electrodes. Of course, one of the electrodes is designated positive, and that's the cathode. The other is designated negative, and that's the anode. Electrons are generated at the anode, making it the site of oxidation, while electrons are consumed at the cathode, making it the site of reduction. And in all Voltaic cells, the electrons move from the anode through an external circuit, like a wire, to the cathode. Why do they flow? Well, there's a difference in potential energy between the electrons at the anode and the electrons at the cathode. Electrons are much like water behind a hydroelectric dam. Well, when behind the dam at altitude, the water is high in potential energy. Excuse me. You open up the gates and the water spontaneously flows down through the dam to a much lower potential energy state. Just as the water spontaneously flows downhill, electrons spontaneously flow from anode to cathode. They pass from reducing agent to oxidizing agent through an external circuit, rather than directly from one species to the other. And that's how we take advantage of the electron flow, by separating the half reactions and by introducing an external circuit. In this respect, the external circuit can be thought of as the dam. The difference in energy per unit charge causes the electrons to flow, and we can measure it. And we call this difference the electric potential energy in volts, units of volts. The total electrical potential energy of the battery is the sum of the potential energies of the cells making up the battery. So again, I had said a battery is a series of individual Voltaic cells joined in series. If you want to know the voltage on a battery, you determine the voltage of any given cell and you multiply with the number of cells in series. A 12-volt car battery, for example, has got 6 individual cells in it that are each just a little higher than 2 volts. A Voltaic cell, then, is an arrangement of 2 half cells connected by either a porous boundary or a salt bridge. And we use the following notation for it. So on the left here, you see the anode, designated the negative electrode, and it's immersed in an electrolytic solution or aqueous paste. The 2 lines represent the separation of half reactions. On the right is the cathode, the site of reduction, designated positive electrode, immersed in an electrolytic paste or aqueous solution. The arrow on top here represents the flow of electrons. That's always from anode to cathode. If that was all there was, you'd have a buildup of negative charge at the cathode. So to equalize charge, we have cations and anions in either a salt bridge or dispersed throughout the electrolytes. And their migration is designed to prevent a buildup of differential charge, negative on the cathode, positive on the anode. So you'll see that cations, which are positively charged ions, follow the electrons, while anions flow in the opposite direction. So here's simple cell notation for a copper-zinc battery. The zinc is the anode, immersed in a zinc nitrate solution. The copper is the cathode, immersed in a copper nitrate solution. And there's a sodium nitrate salt bridge that connects the 2 half cells together. And again, the salt bridge is designed to allow ions to migrate to equalize charge across the battery. And here's an explanation for that. Either a porous boundary or a salt bridge is required to equalize charge between the electrodes, and that's done by allowing ions to pass through it. And of course, we've already seen that the zinc-copper-2 reaction is a spontaneous reaction. We applied the left-hand, right-hand rule to this system using the potential energy table in your data booklet. The left hand was higher than the right hand, and therefore a spontaneous redox reaction occurs between these species. So we can use them to construct a battery, construct two half cells of a battery. In the oxidative side, on the anode, of course, the zinc will go through oxidation. The zinc atom will be oxidized to the zinc ion, and 2 electrons will be stripped off of it. At the cathode, the copper-2 ion will be bound up or react with 2 electrons to form solid copper. There are a couple of general rules we have to follow when we build these batteries. The strongest oxidizing agent will undergo reduction at the cathode, and in this case that's the copper-2 ion. The strongest reducing agent will undergo oxidation at the anode, and in this case that's the zinc atom. And here's a fully labeled diagram for the zinc-copper voltaic cell. I do want to say something about this diagram. I don't own it. I'm claiming a fair use exception to the copyright laws for educational purposes. The reason I'm using it is I couldn't hope to reproduce a diagram of this quality, and I think you deserve to see one. From your perspective, you shouldn't see any advertisements overlaying this video because I'm not able to monetize it. If you see an advertisement, let me know. I'll have it removed. And credit Nelson Chemistry for a wonderful sketch in an equally wonderful textbook. I'm going to try and draw a similar, although not quite to the quality, voltaic cell for the cadmium silver battery. And here's a blank mock-up of the 2 half cells. So on the left, the beaker on the left is the first half cell, the beaker on the right is the second half cell, and the U2 between them is the salt bridge. It contains an ionic compound. So we start labeling. On the left is the anode, the negative terminal, the site of oxidation. And the oxidative half reaction then is cadmium losing 2 electrons to form the cadmium ion and 2 electrons. And the potential for that half reaction is negative 0.40 volts. On the right is the cathode, the positive terminal, site of reduction, and the silver atom, or silver ion rather, is reacting with 1 electron to form the silver atom. And its potential is negative 0.80 volts. So the electrode on the left is solid cadmium, the electrode on the right is solid silver. The cadmium is losing electrons, so it's shedding cadmium ions into solution like this. The electrode on the right is gaining electrons like this. The electrons are flowing from left to right along the external wire. So those are reacting with silver ions in the silver nitrate solution to form solid silver atoms. So what we're going to see here is a cathode, a silver electrode that's going to gain mass as silver atoms are laid down on it. And we're going to see an anode that corrodes, that oxidizes and loses mass as it sheds cadmium ions. And this is typical. Anodes corrode and cathodes build up. Of course, we have nitrate in both electrolytic solutions. The nitrate at the cathode will migrate in the direction opposite to the electrons. And it does so because they're negatively charged. So the electrons repel them. And in fact, they'll migrate up the U-tube towards the anode. The nitrate ions in the anode, half cell, will remain there, and they'll simply stay in locale. They might migrate towards the electrode, but no chemistry is going on there. The salt bridge, we've introduced a salt, and it doesn't matter which salt you use as long as it doesn't interfere with the redox. I've chosen to use sodium nitrate. Sodium ions are positively charged and they're cations, so they follow the electrons toward the cathode. The nitrate ions are negatively charged, so again they migrate towards the anode in the direction opposite to the electrons. Here's the overall redox reaction. And the cell potential, to determine the potential difference of the battery, we subtract the cell potential at the cathode minus the anode. In this case, the cell's got a potential difference of positive 1.20 volts. Oh, I'm sorry. In terms of evidence of a chemical reaction, we're going to see a few things. First of all, the voltage, if we had a voltmeter attached, and this circle with the arrow is supposed to represent a voltmeter, we're going to see a potential difference of a positive 1.20 volts. We're also going to see the anode corrode. So again, the cadmium electrode is going to lose mass. And we're going to see the cathode gain mass. So the silver cathode is going to gain mass. So there's a lot to it, but it holds together if you understand it as a whole. You do 1 or 2 of these in your homework, and you should be up to speed for your exam. The zinc-chloride battery was so named because it was the first to be made within a sealed container. It was named a dry cell. Historically, these were 9-volt batteries, and they were made up of a series of 1.5-volt cells, 6 of them in total. It was simple, inexpensive, and reliable. Ultimately, it was replaced by alkaline and mercury dry cells, which were an attempt to improve on the design. Part of the problem with the zinc battery is the casing was made out of the zinc. It was the anode. So the battery was literally designed to leak and just take your electronics with it when it did. Another problem is that these were not rechargeable batteries. Batteries that can't be recharged are called primary cell batteries, and they can't be recharged because their end products aren't chemically stable. So the end products of the redox, they go on to further react and destroy any ability they might have to run the reaction in reverse. Secondary batteries then are an improvement on primary batteries. They can be recharged, and you recharge them by applying a voltage in the direction opposite to the spontaneous flow of electrons, and you drive the electrons back to the anode. You drive what's called the non-spontaneous reaction. The nickel-cadmium battery, the lead-acid battery, which is used to operate your car, and the lithium-ion cell are all secondary cells. The reaction for the lead-acid spontaneous reaction is this one. So when it's running your car, it's operating as a battery like this. When the alternator is charging the battery, it's running in the exact opposite direction. So the alternator is sending a current back through the battery in the opposite direction to the spontaneous flow of electrons, and it's returning the battery to its initial position, to its reactants. Again, for a battery to be rechargeable, the chemical products must be stable and capable of traveling through an electrolyte to the appropriate electrode. A fuel cell is something different. A fuel cell is an open system, and you're constantly feeding it fuel while allowing waste materials to be removed from the system. The promise of fuel cells is cleanliness and efficiency. However, they continue to be, as they have been for a very long time, under development. Generally, if 2 metals are involved in a redox system, then you can use 2 metal electrodes. However, a lot of batteries use ionic compounds as their oxidizers. For example, an acidic dichromate solution is a strong oxidizer. The problem is you can't introduce solid, say, sodium dichromate as an electrode. It's an ionic compound in solid phase. It's a very poor conductor of electricity. And more importantly, it's soluble in water, so the electrode won't remain in solid form once you immerse it in the electrolyte. So in these systems, instead of using a solid piece of dichromate, for example, we would use an inert electrode, like a graphite rod. And the inert electrode does not participate in the chemistry. That's why it's called inert. It's essentially a physical place, a physical substrate for the redox to take place. Again, dry cells are an example of primary batteries. They're not rechargeable. The common ones are 1.5 volts or 9 volts, and they drive a lot of consumer electronics. Here's an example. This is the manganese 2 zinc dry cell. The cathodic reaction is the reduction you see here. The reaction at the anode is the oxidation here. And here's the overall reaction, 1.55 volts. And again, because the zinc was the anode and the zinc was the casing, as often as not these things would leak and destroy your electronics. And here's the reason they weren't rechargeable, this little asterisk here. The hydroxide produced at the cathode gave rise to side reactions that essentially destroyed the products of this overall redox reaction, and therefore you couldn't drive it in reverse. Nickel cadmium is a very, very commonly used secondary battery. It's rechargeable. Here's the reaction at the cathode. Here's the reaction at the anode, and here's the overall reaction. It's a positive 1.25 volt battery. And again, the products here are stable, so if you apply an external current to this, opposite in direction to the spontaneous flow of electrons, you can force the electrons back up towards the anode. It's like pushing a ball uphill. When we say that here, you apply an external circuit to a secondary battery and you drive electrons back to the anode. And you're in effect causing a non-spontaneous chemical reaction to take place. Lead storage batteries are also secondary batteries. Typically, car batteries are lead storage batteries. Both electrodes sit in an electrolytic solution with sulfuric acid. Here's the cathodic reaction. Here's the one at the anode. We add them up, and you'll see that each cell generates positive 2.04 volts. Of course, your car battery is 12 volts, so it would have 6 individual cells arranged in series to generate the 12 volt potential difference. Of course, the alternating recharge is responsible for recharging the battery while it's in operation. It does so by, again, driving electrons back towards the anode. Fuel cells must be supplied with a continuous flow of fuel, and they must also provide that waste material of the reaction can be allowed to leave. One sort of promising type of fuel cell is the hydrogen-oxygen fuel cell. Hydrogen is pumped in at the anode, oxygen is pumped in at the cathode, and pressure is used to push the hydrogen through a catalyst to split it into hydrogen ions and electrons. The electrons move through an external circuit towards the cathode, which generates the electrical energy. The oxygen is also pushed through a catalyst, forming 2 oxygen atoms, and the hydrogen ions react with the oxygen atoms to form water. So here's the reaction at the cathode, the reduction of oxygen. Here's the reaction at the anode, the oxidation of hydrogen gas, and here's the voltage. So each cell is generating positive 1.23 volts. And here's the promise of fuel cells. The only waste material coming out of the tailpipe of these vehicles, for example, is water. The complication and the hesitation is this. Fuel cells need a source of hydrogen. And when we manufacture hydrogen, we do so by reforming methane or methanol. The other end product of the process is carbon dioxide, which is a greenhouse gas, of course. So while operating the fuel cell is clean, manufacturing the fuel for it is not a clean process. And I think that ends my lecture. Just one last comment. Even though the manufacture of the fuel here is not a clean process, these fuel cells are typically much more efficient than gas engines. And we see that here, sort of 24 to 32% efficient, as opposed to a gas-powered engine, which is 20% efficient. So that concludes my lecture. I hope you found it of some value. I'd refer you to any homework that your teacher assigns in this area, and we'll see you next time when we talk about electrolytic cells. Thank you.